Assalamualaikum and hello everyone. Welcome to this video on the mechanical and thermal properties of nanomaterials. In this video, we will explore the unique behaviors they exhibit at the nanoscale, why these behaviors matter, and how we use this knowledge in advanced technologies, including electronics, medical devices, and biomaterials. Let's begin by understanding what nanomaterials are. Nanomaterials are materials that have structural features like particles, fibers, or grains that are smaller than 100 nanometers. Just to give you a sense of scale, 1 nanometer is a billionth of a meter. That's about 100,000 times smaller than the width of a human hand. At this incredibly small scale, materials behave differently. Why? Because of 3 key reasons. First, high surface to volume ratio. Second, quantum confinement effects. Last one, atomic scale structure confinement. These nanoscale characteristics give rise to new mechanical and thermal properties, making nanomaterials useful in electronics, coatings, drug delivery, and even tiny devices like MEMS and NETs, micro and nano electromechanical systems. Now, let's talk about nanomechanics, which is the study of how material behaves mechanically at the nanoscale. While traditional mechanics focuses on how materials stretch, bend, or break under force, nanomechanics goes much deeper, literally looking at how these behaviors change when the structure of the material only a few atoms swell. In nanomechanics, we study stiffness, strength, elasticity, and plastic deformation. To study these tiny materials, we use advanced tools like atomic force microscopy (AFM), which can feel the surface of a material at the atomic level. Nano indentation, where a tiny tip presses into the material to measure hardness and stiffness. PEM-based strain analysis, which uses electron microscopes to watch atoms move under stress. This field is crucial of designing reliable nano devices and materials with specific mechanical functions. When it comes to elasticity, nanomaterials behave in ways that challenge traditional mechanics. At the nanoscale, surface atoms dominate the behavior. These atoms don't have neighboring atoms on all sides like atoms in the bulk. This means they have unsatisfied chemical bonds and different energy states. This leads to surface stress, like an internal tension that changes how the material bends or stretches. Elastic modulus changes. The stiffness of the material can either increase or decrease depending on how surface atoms are arranged. Interestingly, these changes become especially noticeable when the material size drops below 50 nanometers. For example, a gold nanoparticle might have a different stiffness than a bulk of gold bar, even though they are made of the same atoms. The outcome depends on material type and surface chemistry. In some cases, nanomaterials deepen, while in others they soften. One of the most well-known effects at the nanoscale is size-dependent elasticity. This means the mechanical properties, especially stiffness, change as the material gets smaller. Why does this happen? First, because of reduced defect density. In small volumes, there is less chance for defects like dislocations or voids to form. Second, surface stiffening. As mentioned before, surface atoms can enhance the stiffness. As a result, nanostructures like nanowires, nanotubes, nanoparticles often exhibit higher stiffness than the small material in bulk form. Third, atomic structure. Nanomaterials tend to have fewer dislocations, making them more elastic and stronger. Fewer grain boundaries, which means less internal noise to weaken the structure. However, in nanocrystalline materials, grain boundaries can do two things, which is weaken stiffness by adding acid points or impede dislocation motion, which actually increase strength. Next, at sizes below 10 nanometers, quantum effects start to kick in. This is especially true in metals and semiconductors. Here, the electrons are no longer free to move as they do in bulk materials. Their behavior is restricted or confined, which changes how atoms bond and how energy is distributed in this material. This quantum confinement affects elasticity by modifying the electron cloud around atoms and changing bond strength and bond angles. So while classical mechanics still applies in many cases, we must also consider quantum mechanics at the very small scale.
In understanding how nanomaterials behave under stress, it is important to consider several key factors that influence both fracture and deformation. First, the size effect. Smaller material has more surface area exposed, which change how they handle stress. Second, temperature. It affects how easily atoms move, especially through dislocation and grain boundary sliding. Third, strain rate. When materials are deformed quickly, they are more likely to break in a brittle way. Lastly, material properties. Different materials behave differently depending on their structure and strength. In conventional material, plastic deformation primarily occurs through the motion of dislocations, which are line defects that enable layers of atoms to slide past one another. However, in nanomaterial, this mechanism is significantly altered due to their extremely small dimensions. The volume available to accommodate dislocations is greatly reduced, and the likelihood of pre-existing dislocation is low. As a result, any dislocation that do form are typically nucleated at surfaces or interfaces that are often annihilated immediately after. This leads to phenomenon known as dislocation starvation, where the materials become stronger because it cannot undergo the plastic deformation in the typical way. This behavior is commonly observed in nanostructure such as nanopillars, nanowires, and thin films subjected to comprehensive or tensile loading. In nanocrystalline materials, where the grain size is less than 100 nanometers, grain boundary makes up a substantial portion of the material is volume. As a result, the dominant deformation mechanism shift away from traditional dislocation glide and instead rely on grain boundary mediated process. These include grain boundary sliding, grain rotation, and grain boundary migration. While these mechanisms enable deformation to occur even at low strain rates, they also tend to promote strain localization. This concentration of strain in specific region can ultimately lead to premature failure of the material. As a result, once the critical stress is reached, cracks can propagate rapidly, leading to catastrophic brittle failure. In terms of fracture mechanism, brittle fracture through cleavage is more commonly observed in nanoparticle and nanowire, where dislocations are either absent or ineffective. However, in certain nanocrystalline materials, bond nucleation and growth can still take place, resulting in a modified form of ductile fracture. Although this void coincidence mechanism is less dominant than in bulk materials, it still contributes to overall fracture behavior of some nanomaterial. First, we have the Hall patch breakdown. The Hall patch relation states that strength increases as grain size decreases. However, when the grain size drops below around 10 to 15 nanometers, this trend reverses. This is known as the inverse Hall patch effect. It happens because grain boundary mediated mechanisms start to dominate, reducing the overall strength. Second, strength approaching theoretical limits. Nanomaterial, especially defect-free nanowires or nanocrystal, can reach strength close to the theoretical limit, which is roughly 1/10 of the elastic modulus. This is something bulk materials can't achieve due to the presence of pre-existing defect. Lastly, strain rate sensitivity. Nanomaterials often show enhanced strain rate sensitivity. This means their deformation behavior becomes more time-dependent, particularly in process involving thermally activated grain boundary mechanisms.
Talking about how thermal conductivity and heat transfer behave in nanomaterials, materials that have structural size between 1 and 100 nanometers. These materials are very different from their counterparts due to their extremely small size, high surface area to volume ratio, and dominant quantum and interface effects. Let's begin with the basics. What is thermal conductivity? Thermal conductivity, is the material's ability to conduct heat. In nanomaterials, heat is mainly carried by photons. These are vibrational energy packets in atomic lattice. In metals, heat is also by electrons. However, at the nanoscale, this mechanism behave differently due to frequency scattering and quantum effects. There are several key mechanisms of heat transfer in nanomaterials. First is conduction. This is the dominant mode in nanomaterials. Photons can scatter at numerous more frequently, lowering conductivity. Sometimes photons travel without scattering. This is called ballistic conduction, a behavior not typically seen in bulk materials. Second is interface effects. Nanomaterials have many grain boundaries and interfaces. These interfaces create a thermal resistance known as capillary resistance, which limit heat flow. Third is electron contribution. In metallic nanomaterials like gold nanowires, electrons also scatter at the surface, reducing conductivity. While the white domain Franz law still applies, nanoscale correction are necessary. Lastly is radiation and convection. These are minor within solid nanostructure but become important in nanofluids or porous materials where fluid motion or surface radiation contributes to heat transfer. Now, let's look at how these properties can use in real-world application. First is nanofluids. These are fluids that contain suspended nanoparticles. They offer much better thermal conductivity than traditional fluids. But if too many nanoparticles are added, viscosity increases with a fast flow. Nanofluids are used in electronic drilling, heat exchanger, and renewable energy system. Second is thermoelectric materials. In thermoelectrics, we want low thermal conductivity but high electrical conductivity. Nanostructure have achieved this. For instance, argentum, lead, antimony, tellurium nanomaterials can reach very low thermal conductivity, around 0.3 watts per meter Kelvin, while still producing good electrical output. To summarize, thermal conductivity in nanomaterials is governed by size, surface, and quantum effects. This unique behavior opens up exciting possibility in heat management and energy conversion.
Let's begin by understanding what a phase transition is. A phase transition is a rapid transformation of a material from one state of phase to another. Common examples include melting, where a solid becomes liquid, boiling, where liquid turns to gas, and transition between different solid phases. These changes involve rearrangement at the atomic or molecular level and are marked by abrupt changes in thermodynamic properties such as discontinuous in Gibbs-free energy derivatives. In bulk material, phase transition occur at a different temperature or pressure. For example, the melting point of bulk metals. However, nanomaterials behave differently due to their extremely small size and high surface to volume ratio. Interestingly, some materials that are non-magnetic in bulk become magnetic at nanoscale, indicating unique phase changes. Moreover, nanomaterials can stabilize metastable or entirely novel phases that do not exist in bulk forms. Nanomaterials exhibit several unique features during phase transitions. First, phase stability depends strongly on particle size. For instance, smaller nanoparticles often require higher pressure to undergo phase transitions. A good example is the transition from bachromite to hematite, where the transition pressure increases as particle size increases below approximately 7 nanometers. Second, nanomaterials can stabilize metastable and novel phases due to their high surface energy and altered thermodynamics. Third, phase transition in nanomaterials often coupled with changes in mechanical stiffness or molecular theory. This coupling makes them highly sensitive to external stimuli and useful for multifunctional applications. Onto melting behavior, nanoparticles generally melt at lower temperature than their bulk counterparts. This melting point depression happens because surface atoms have fewer bonds and thus require less energy to become mobile. This effect is nearly universal for nanoparticles and is driven by the lower surface energy of the liquid phase compared to the solid. So the high fraction of surface atoms also enhance atomic mobility and alters melting dynamics, fundamentally changing how melting occurs compared to bulk materials. These changes have important implications for the thermal stability of nanomaterials. When designing nanoscale devices, catalysts or sensors, we must consider this. This reduces melting points and alter phase transition behavior to ensure reliable performance under thermal stress. Finally, phase transitions in nanomaterials can be precisely controlled through phase engineering. By tailoring size, shape, and composition, we can stabilize specific phases or induce transition at targeted conditions to optimize material properties. This control is crucial for applications such as enhancing catalytic activity by exploiting phase-dependent surface properties, improving electronic device performance through phase control conductivity of magnetism, and the last one is developing sensitive sensors that leverage phase change-induced property shifts. This ability to engineer phase transitions opens exciting pathway or advanced technologies. So in summary, phase transition and melting in nanomaterial differ fundamentally from bulk materials due to size effects, surface energy contributions, and coupled physical properties. Understanding and controlling these phenomena is key to unlocking the full potential of nanomaterials in various technological fields.